Every day, countless mysteries of the invisible world are solved by a groundbreaking tool, gas chromatography. From the purity of the air we breathe to the quality of the food we eat, this ingenious technology touches every aspect of our life. But how does it work? And why is it so essential? Let's unravel the story of gas chromatography. The origins of gas chromatography trace back to the mid-20th century. Scientists Archie John Porter Martin and Richard Lawrence Millington Sain revolutionized chemical separation techniques, earning the Nobel Prize in Chemistry in 1952. Their pioneering work laid the foundation for modern chromatography. Soon, the principles they developed were adapted to gas chromatography, enabling the analysis of volatile compounds with unparalleled precision.
A typical GC system has three key components. First, the mobile phase. This is a carrier gas, often helium, nitrogen, or argon, that transport the sample through the system. Second, the stationary phase, a column located in a temperature-controlled oven where the separations of compound occur. Third, the detector. Devices like the flame ionization detector FID measure analyze in the gas stream. Samples are introduced into the system through an auto-sampler or manually using a shrink. The injector, a heated chamber, volatilizes the sample and its matrix. In split mode, a portion of the sample is diverted out through a split vent. In splitless mode, the entire sample enters the column.
Two types of columns are used in GC. First, packed columns. The stationary phase is directly coated within the column. Second, capillary columns. The stationary phase is coated along the inner wall of the column. The separation occurs based on how each component partitions between the mobile and stationary phases. Components with less affinity for the stationary phase travel faster and elute first. Conversely, components with greater affinity interact more and elute later. Factors like column temperature, carrier gas flow rate, column length, and sample amount influence the separation process. As compounds exit the column, they interact with the detector. One commonly used detector is the flame ionization detector, or FID. In the FID, organic compounds are combusted in a flame generated by hydrogen and air. This produces ions, primarily carbon ions, that generate a current. The current is proportional to the quantity of the organic compound. The data is displayed as a gas chromatogram, where the x-axis represents the retention time, showing how long it takes analytes to pass through the column. The y-axis reflects the quantity of each analyte represented by the area under the pit. Advantages of gas chromatography: high resolution and precision. The high resolution enables accurate analysis of complex mixtures, enabling the accurate detection and quantification of analytes within a sample. Speed and efficiency. Despite its speed, it does not sacrifice the accuracy of outcomes, providing a high degree of precision even in rapid analysis. Sensitive and versatility. The ability to apply GC to numerous volatile and semi-volatile compounds makes it an indispensable technique in multiple scientific fields.
The disadvantages of gas chromatography: cost and complexity. The purchase of mass GC equipment can be high and requires skilled operators to produce proper results. Next, sample limitation. Non-volatile compounds cannot be analyzed directly without prior derivation, limiting the scope of GC applicability.